In a vacuum, light travels in a straight line at constant speed unless it encounters matter. If it does encounter matter and enter a medium, the light slows down. The material's index of refraction measures how much light slows down in a material. For a given material, the index of refraction n is equal to the speed of light in a vacuum c, which is 3 times 10 to the 8th meters per second, over v, the speed of light in the material. In this expression, the value of n and the speed of light in the material are inversely proportional. So for small values of n, light's going to be traveling faster, where for a larger value of n, light's going to be traveling slower. Now, because the index of refraction is the speed of light in a vacuum over the speed of light in the material, the value for the index of refraction in a vacuum is simply equal to 1. So when light travels from one medium to the next, it changes speed. This change in speed in light causes the light to change direction. Refraction refers to the process by which light switches direction when going from one medium to another. When light slows down, it goes from a medium with a lower refractive index to a higher one. The light slowing down causes the light to bend towards the normal. In math, normal is used to mean perpendicular. So the normal line is perpendicular to the interface between the two mediums. When light speeds up and goes from a high refractive index to a low refractive index, it bends away from the normal. This is an example question that gives 3 materials and asks to rank the indices of refraction in the 3 materials. The formula for index of refraction says that the index of refraction is the speed of light in a vacuum over the speed of light in a material. So the faster light travels in the material, the smaller the index of refraction is going to be. And then I also know that if the speed of light in the material is faster, then light is going to bend more. So if I look over here, N2 is the material where light is bending away from the normal line here the most, which means that if N2 has the fastest light, it has to be the smallest index of refraction. Meanwhile, in N1, here the light is bent most towards the normal, which means that N1 is going to be the slowest and have the largest index of refraction. Snell's law was first discovered by the Dutch scientist Willebrord Snellius, or simply Snell. Snell's law relates the indices of refraction of 2 materials that light travels between to the angles of incidence and the angles of refraction that light makes in the 2 materials. In both cases, the angles refer to the angle made with the normal line. Snell's law states that index of refraction 1 times the sine of the incident angle equals index of refraction 2 times the sine of the refracted angle. In this example, light travels from air into a piece of glass. It gives the angle of incidence of 30 degrees and the angle of refraction being 20 degrees. And part A is asking for the index of refraction. So this is going to use Snell's law, where N1 refers to air and N2 refers to the glass. So N1 sine 30 degrees equals N2 sine 20 degrees. So solving for N2, I get that N2 is N1 sine 30 over sine 20. Because the glass starts in air, I can set N1 equal to 1 and get an index of refraction for the glass of 1.46. Part B asks for the speed of light in the glass. So index of refraction is defined as the speed of light in a vacuum over the index of refraction in the material. So in this case, 1.46 is the speed of light in a vacuum 3 times 10 to the 8th over the speed of light in the glass. When this is solved for the speed of light in the glass, the answer is 2.05 times 10 to the 8th meters per second. Part C asks for the frequency and wavelength of the refracted light. So the wavelength of the original light was 600 nanometers. Using speed of light equals f lambda, I get that the frequency is speed of light in a vacuum 3 times 10 to the 8th over the wavelength 600 nanometers, and that's going to be 5.1 times 10 to the 14th hertz. Now when light goes between two mediums, the frequency is going to stay the same. So the frequency when the light gets to glass is the 5.1 times 10 to the 14th hertz. But since the speed of light changes, the wavelength's also going to have to change. So in the new medium, glass, the speed in the glass equals the new wavelength of light times the frequency. So solving for wavelength, I have the speed of light in the glass over frequency, and then just plug in numbers. And I get a wavelength of 4.9 times 10 to the negative 7 meters. When light goes from a high refractive index to a low one, where it would try to speed up, it's possible that none of the light is refracted. This is called total internal reflection. Total internal reflection occurs after the angle of incidence has exceeded some maximum angle, called the critical angle. If the incident angle is above the critical angle, all the incident light is reflected, with none of it being refracted. At the critical angle for total internal reflection, the incident light will travel parallel to the surface between the two interfaces. So the intended angle of refraction will be 90 degrees. So to find the critical angle, going from a slow medium N1 to a faster medium N2, Snell's law states that N1, sine of the critical angle, equals N2, sine of 90 degrees. Because sine of 90 degrees is 1, the critical angle can be solved for by taking the inverse sine of N2, the faster median, over N1, slower median. This example looks at a person standing at the edge of a pool and looking at a coin at the bottom of the pool. Now, if the person does see the coin, they're going to see light coming from the coin, refracting through the air, and then coming into their eye. So if I continue the line coming from the water surface to their eye, it's going to lead to the apparent position where they would see the coin. So when the person looks at the water into the coin, they're not going to see the actual position. Now, if the angle of incidence going from water to air is too big, the person won't see the coin at all. And the question is asking for the maximum angle for which that happens. So if you have light coming from water to air, I would have N1 for water times sine theta in water equals N2 of air times sine of the angle in air. And at the critical angle, the angle of refraction is going to be 90 degrees. So the index of refraction of water is 1.33. Sine critical angle equals 1 sine 90 degrees, which is 1. So I get that the maximum angle is inverse sine of 1 over 1.33, and that's going to be 49 degrees. In the last example, a laser beam is shown on two different blocks of material starting from air, and the graph plots the sine of the incident angle, theta 1, versus the sine of the refracted angle, theta 2, and it gives the best fit line of the graphs for both blocks. Now, since this graph is coming from air, using Snell's law, I get N1 sine theta 1 equals N2 sine theta 2. And here, N1 is from air, so it's equal to 1. So the equation becomes sine theta 1 equals N2 sine theta 2. Now this equation is already in slope-intercept form, y equals mx. So I plot sine theta 1 on the y-axis and sine theta 2 on the x-axis, which means the index of refraction of the block N2 is equal to the slope of the graph. So looking at the graph, block 1 has a steeper slope, so it has a greater index of refraction.